Hey there. We're going to go over some notes for freefall, or objects that are in freefall. And so what classifies an object to be in freefall is whenever gravity is the only force on the object. And so when this is the case, the acceleration that's taking place is because of gravity. So let's kind of see where this comes from. If I have a ball or some kind of object and I drop it, and we would draw a free body diagram while it's in the air falling. The only force that we would have would be our Fg, right? And we're assuming here there's no air resistance or drag, then that's the only force that we'd have. And if we make our free body or our net force equation in the y direction here, it's just going to equal Fg. Now let's do some substitutions that we learned last semester. And Newton's second law says acceleration is the net force divided by the mass. And we could rewrite that for net force, and that's equal to mass times acceleration. So we could substitute this for our net force. We also learned last semester how to calculate the weight of an object in newtons, and it's just m times g. So we could also substitute that in for the weight. And doing those substitutions, it would give me ma is equal to mg. Now my mass cancels, and so the acceleration of this object that's falling is just equal to g, which is 10 meters per second squared. And so that's where this comes from, that the acceleration of an object that's in free fall is equal to 10 meters per second squared. Now, not every object that's falling is in free fall. And we've seen this at the beginning of the year. If you remember, we did our Aristotle lab. And in our Aristotle lab, we said, do heavier objects fall faster? And what we found was that, they all fall the same rate, but sometimes air resistance or drag could cause an object to fall slower, right? So the key there was that in those cases, there was another force, right? We had a drag force or air resistance taking place. But if Fg is the only force on this object that's falling, then we consider that to be free fall, and the acceleration is just equal to g, or 10 meters per second squared. Now, there's another case where an object is considered to be in free fall, and that's whenever we throw an object straight up in the air, right? So let's say that I'm kind of standing here, and we have a ball, and we throw this ball straight vertically into the air. Well, again, drawing a free body diagram of that ball, we would only have Fg here. So it's the same situation where the gravity is that only force on it. And so the acceleration is going to equal 9.8. Now, if we throw the object up with an initial velocity, let's say v naught, and we call that a positive velocity, then that means that my acceleration is going to be negative g, because this acceleration, it's pointing downwards. So typically, if you have a problem where you're throwing an object straight in the air, you have a positive v naught, or initial velocity, so you're going to have a negative acceleration of negative 10 meters per second squared. Also in this situation, when it reaches its max height, so let's say our ball is right here, and this is the max height. At the max height, our final velocity is equal to 0 meters per second. So we could set, that's an assumption that we make if you have a problem and it's telling you and you're looking at the max height of an object thrown straight up in the air, we know that the final velocity is going to equal 0. Now, eventually that object is going to reach a max height, and then it's going to return and start falling back down. I'll kind of draw it over here on the side. And once it reaches where its initial position was, where the initial velocity was, at that point right there, our initial velocity is going to equal our negative final velocity. And that is whenever it reaches this initial height here that it was thrown from. Now, graphically, we can look at this situation too. So let's make a position time graph for this object here that we threw straight up in the air. So what it would look like is it goes straight up in the air, it reaches a max height, and then it starts to fall back down to its original height. So if you have a position time graph, that's what it would look like. And we did our stations lab, and you should have found that when you threw your ball in front of the motion sensor that you had this kind of parabolic shape for your position time graph. And for a velocity time graph for this situation here, and if you remember from the lab with the motion sensor, you had an initial positive velocity, and then it moves here, gets closer and closer to your zero, and then continues to go straight through. Now, at this point right here, your velocity is equal to zero. And looking back at our drawing, our velocity equals zero at the max height. So this point right here would be your max height. And if your initial velocity is here, this final velocity right here, remember your initial velocity would equal your negative final velocity. So that's what it would look like graphically if we were to look at an object being thrown vertically into the air and then it fall back down. Now, there's another thing too to kind of make note, and that is whenever you're at this situation here where the ball or the object returns back to that initial position, my change in vertical position is equal to zero. So sometimes in a problem, in one of these kind of free fall problems, they won't necessarily tell you your displacement is zero, but they'll tell you it, it ends where it started. So we need to understand that your displacement is zero, or they won't tell you your velocity is zero at the max height. They'll just say the max height. So you just got to make those assumptions there and interpret the problem to get those variables. So let's work a problem together. So this one says a ball is thrown up vertically from the ground level and it has an initial velocity of 20 meters per second. So we're going to use this guess method to solve here. So your initial velocity is equal to 20 meters per second. It says how far is it from the ground at 1 second and then again at 3 seconds. So let's start with the 1 second. Now remember, we need 3 pieces of information to use our kinematics here. And that third piece, since it's a free fall, remember your acceleration is equal to g. And in this case, it's going to be a negative 10 meters per second squared. Now, let's kind of draw it out and look. We threw it with a positive initial velocity, and it goes straight up. Drawing the free body diagram, your FG is pointed down, so it's going to be in the negative direction. So that's why we call that negative 10 meters per second squared there. And your unknown, back to using that guess method, that's going to be our, our unknown information. We're trying to solve for our delta y, our change in vertical position here. And so the variable that we're missing from here would be my final velocity, right? We don't care about our final velocity. So the kinematics equation that we need to use here is going to be one that doesn't have that. And so the one that we have is delta y is equal to v naught t plus 1/2 at squared. And we're already kind of set up for delta y, so we could just plug in our numbers here and solve. So it's going to equal your initial velocity, which is 20 meters per second, times 1 second plus 1/2 times negative 10 meters per second squared. My time is 1 second, and that's squared. So 20 times 1, that's just going to be 20 there, and our seconds is going to cancel. So that'd give me 20 meters plus we have 1 squared is just 1, and then my negative 10 there. So that gives me, and half of that, negative 5 meters. So your delta y, or your vertical position there, is going to be 15 meters. So that was for 1 second, but the problem wanted me to find both 1 second and 3. So let's go ahead and solve for the position at 3 seconds. So your initial velocity is still 20 meters per second. Now my time is going to equal 3 seconds. Acceleration is still equal to negative 10 meters per second squared. So we're going to use the same equation because we're solving for this delta y still. So using this same equation, v naught t plus 1/2 at squared. We can start plugging in our numbers. So 20 meters per second times 3 seconds plus 1/2 times negative 10 meters per second squared times 3 seconds, and that's squared. So then I'm going to be left with 60 meters minus, so 3 squared is 9, 9 times that negative 5 would be negative 45 meters, so we subtract them. So your vertical position here is going to be 15 meters. But wait a minute, that's what it was at 1 second. So what does that mean? That means that at 1 second, the ball was moving up and your vertical position was 15 meters. And then between 1 and 3 seconds, the ball went to its max height and started to fall back down, and it was back at the 15 meters. So for this first part, the 1 second, this is when it was on its way up. And at the 3 seconds, it's when it was on its way down. All right, so hopefully this helps a little bit with our free fall notes, and then next time we'll start talking about horizontal projectile motion.